Hello, everyone. My name is Michael Fitzgerald, and I am the author of the article entitled Estimating Dyad Level Processes in MFT Research, General Overview of the Common Fate Model and Extensions into Mediation, Moderation, Growth, and Hybrid Models, published in the Journal of Marital and Family Therapy. In this video series, I am going to be walking through each of the different analyses that I talked about in the article and show you all how to estimate those different models using a video tutorial. In this first video, what we'll be doing is we'll be estimating the common fate model, as well as getting a general introduction to M+ for those of you who may be less familiar. So we will start with an introduction to M+. So I will first share my Finder window. I will be using a Mac, so it might look different if you have a PC. But what I'm showing you here is my folder with all of my M+ input and output files, as well as my data file. So what I do is I have all my input files and my data file in the exact same folder. So I've highlighted the .imp file, which is my M+ syntax file, and I have my data2.dat, which is my data file. So I have these in the exact same folder because M+ by default will automatically go look for your data file in the same folder. And if it can't find the data file in a specific folder, then it's going to give you an error message. But if you want to keep your data file in your input file for whatever reason, data security, then you can actually keep them in separate folders. But then in the M+ syntax, you're actually going to manually specify the exact place and where your data file is located. Okay, so we will not be doing that because I'm going to have the input and the data file in the exact same folder, just for ease of use. And this tends to be how I run my analyses. So next, I will open up the first figure that you will see in the article. And so this is the first figure where I outline the actor-partner interdependence model and the common fate model. And so what we will be doing in this first video is estimating what is happening in panel B. And this is the baseline common fate model with a one independent variable and one dependent variable. Right? So now let's shift over to M+ to begin to estimate these different analyses. So this is M+, and I'll briefly provide an introduction to what all is going on here. So in the title, that is the title of your data file, and this can be anything. You can create any type of title, and you don't even have to have a title. Oftentimes, I will just title my my syntax with some very specific descriptions or descriptors, so that if I'm using multiple syntax files, I actually know what my analysis is doing. I don't actually have to go into the actual syntax to figure out what is actually happening. Right? This is also a place where I will take notes. So in my different models, I might have some non-convergence. I might test a couple of different models together. I might actually use different data files as for like sensitivity analyses or subgroup analyses. And I will actually use that, make those notes in the title. All right. So data, this is telling M+ what my data file is titled and the format that it is in. And so my data file is actually called data2.dat, right? So this is a .dat file. And I am telling M+ that my input, baseline cfm.imp, and data2.dat are in the same folder, right? So under the variable command, I first start with names R, and then I list off all of the variables that are in the data set, right? And so what you will notice about my coding scheme is I have an _m after every variable that is reported on by a male partner. And you will notice I don't have that for the female partner. So if you see an _m, it means male. And if it doesn't have that, it means that it is the female partner. In this analysis, in these data, we have 305 heterosexual couples. I have excluded the heterosexual or homosexual couples. I have eliminated the gays and the lesbian couples because they are indistinguishable. And so what we are actually going to be doing here is we want to use distinguishable dyads, and then we're also going to test indistinguishability. And so what you will, again, what you will notice is that I have very short variable labels. So M plus, one of the nuances of it is that it only allows you to have variable names that are 8 letters or shorter, and you separate each variable by a space, right? So you will have to get creative with your variable names when you are using M plus. You will also notice that I have commented out, use the exclamation point and a 5, and you see some green text. What that represents is me telling M plus to ignore everything on the right-hand side of that exclamation point. And what these numbers are is just the number of variables that are on that line. And this is a way for me to double check when I'm importing my data that I have specified the correct number of variables. Otherwise, M plus will give you an error message, something to the effect of this, the data file has come to an unknown ending or something to that effect. And so that generally means that you have too many or too few variables in your data set that may or may not actually be there. So scrolling down, we're going to next look at the use variables um, um, sub command within the variable command. So what the use variables are command is I'm telling M plus I'm only going to use these 4 variables. We have 70 something variables in the overall data set, and I'm only telling M plus I want to use these 4 variables. All right. So whatever variables are going to be included in your analysis, you want to tell M plus that they are going to be included there in this use variables command. And if you don't, then M plus will give you an error. We also have missing data. So this data set actually has relatively little missing data, but we do have a few cases. And what I've done in my data management is I've specified all those missing values to be -999. And so I am telling M plus that ignore -999 and treat it as missing, not an actual value. If I didn't specify this and I have that missing data code of -999 in my data, then M plus would treat those as real values and my model may not converge or I get really wonky estimates. I also have an ID variable. So this is the dyad ID. So this is the identifier that links the male and the female couple together. So this is again a level 2 variable. And you don't need this, but I always specify an ID variable because sometimes it's nice when testing outliers and taking testing sensitivity analyses to be able to know which cases to remove. And this is a really easy way of doing that. So I always include, again, an ID variable. So in the analysis command for this first model, we are going to be using robust maximum likelihood. So this is regular maximum likelihood, full information maximum likelihood. And then what we are doing with robust is we are going in kind of after the fact and making a correction to the chi-square and to the standard errors to account for non-normality in the residuals. One of the assumptions of structural equation modeling is we have multivariate normality in the residuals, and very rarely, especially with couples research, will we ever accomplish that. So I am going in and I want to make an adjustment to the standard errors so I don't end up with a type 1 error. So that is what MLR is. Regular maximum likelihood is the default in M+. So it just be estimator is ML, but we are going to use, again, robust that has the Yuan and Bentler correction, which is also known as a scaling correction factor. So in the model command, we are first going to estimate our measurement model. So in the common fate model, we are estimating a dyad level process. And what we are going to do is fix both of the loadings for partners to be 1. And we are going to be fixing the unstandardized loadings to be 1. And what this is doing is it's estimating that dyad level process. Essentially, it's going to be a dyad level mean since we're equally weighting men and women. So we fixed these to be 1 for a couple of reasons. One is for identification. If we freely estimated these factor loadings, then our model would actually have negative degrees of freedom and it would not converge. But also, we are estimating a diet level process that is equally indicated by men and women. And so we are going to be estimating that by fixing the factor loadings to be equal. Right? And so in M plus, we have our latent variable right here, which I'm calling diet cope. And then the by statement, that tells M plus that we have a latent variable and that every variable on the right-hand side of that, up until the semicolon, is going to be an indicator of that latent construct. And you'll notice that every line in M plus ends with a semicolon. So that tells M plus to stop the command and move on to the next command. Right? And so we are going to do that for both dyadic coping and relationship quality. So this is the common dyadic coping subscale from the dyadic coping inventory. And then this is the couple satisfaction index, the 4-item from Funk and Roget in 2007. Right. So we're going to be estimating dyadic coping at the dyad level and relationship quality at the dyad level. And both of these variables are measured using relationship referential items. So what we're going to do next is estimate our model, right? And so what we are actually going to do is estimate the effect of dyadic coping on relationship quality at the dyad level. And so what you do is you have your dependent variable on the left-hand side, and you have your independent variable on the right-hand side. And then your on statement is M plus language for regression. All right. So this means that CSI at the dyad level is being predicted by dyadic coping at the dyad level. So dependent variable, independent variable. All right. And then we also want to estimate these within-person covariances. So in the common fate model, we have male reports on both dyadic coping and relationship quality, and we have female reports on both dyadic coping and relationship quality. So what we need to do is we need to correlate those errors for men and for women, because there might be a reporter effect. There might be some unknown explanation that's not in our model that might be influencing how men perceive both of those variables and how women perceive both of those variables. For example, males' personality or neuroticism might be influencing how they respond to the CSI and the dyadic coping, and we want to account for that using those residual covariances. Also, this is another way to account for potential bias in the regression coefficients, because if there isn't that covariance there or estimated and we run the model, that means our regression coefficients may be biased. Right? And at the very bottom, we have the output. So the output syntax is going to be relatively straightforward. We're going to have SAMSTAT, and what this does is give us descriptive and bivariate statistics and information, means, variances, skewness, kurtosis, covariance coverage. Essentially, that can be thought of as, the extent of missing data, your correlations, your covariances, and things of that nature. Residual will be the residual variance covariance matrix. And that is a way of estimating local misfit in your model, where your model is your fully saturated model is being compared to the model that you estimate. Right. Then Tech 1 is going to be the labels on your parameters. So each parameter in the model is going to have a specific number associated with it. That way, if we get an error message and it says problem with parameter 43, we can go to our Tech 1 output and we can see what the problematic parameter is, whether it's a mean, a variance, or a covariance. Tech 4 is going to be our variance covariance matrix. We have our STDYX, which is going to be our standardized outcome. So STD means standardized, and then Y and X means standardize your X variable and your Y variable. Mod indices are, since we have an over-identified model, we're going to have a 1 degree of freedom. That means that there might be some form of misfit in our model, And what we are going to do is estimate, if we add in a potential parameter that we didn't originally implement, it'll improve the model by such and such amount. And what this model-in-series will do is say, if you add in this covariance or this regression or estimate this mean, it's going to improve your model chi-square by this amount, right? C interval is going to be your 90, 95, and 99% confidence interval. That will matter a little bit less here, but when we start talking about mediation, these intervals become more and more important, particularly when it comes to bootstrapping. All right. So that's a brief introduction to M+ and to our model. And now we can go ahead and we can estimate and run this model. And so M+, the model will run fairly quickly. And so we'll scroll down, and M+ gives us your syntax first. So it'll give you out your input file again. All right. And then you'll also notice that I got some warnings. All right. And so what these warnings are saying is that some of these input lines exceed 90 characters. M+ will only read the first 90 characters in any given line. So if your syntax is longer than 90 characters, you just have to move to the next line and don't include a semicolon. All right. But this will not be problematic for us because the lines that include 90 or more parameters or characters down here, these two lines, they are commented out. So M+ is already kind of ignoring them. That's not being fed into our results. So these are ignorable warning signs. Okay. And so we'll scroll down and we'll get a summary of the analysis. Number of groups, since we're only estimating one group. This is the number of dyads, since these data files are going to be in wide format. So you're going to have a column for male relationship quality, and right next to it, you're going to have a column for female relationship quality. And your case number is going to be the dyad ID. All right. So we have 4 continuous variables, and then we have our estimator, and then we have all of these other pieces of output, which aren't necessarily of great interest to us here. We have covariance coverage, and this is the amount of pairwise covariance coverage or percent of missing data that we have in our sample. So this means for dyadic coping for women, in dyadic coping for women, right, that the amount of that percentage of complete data is 99.3. So that means we are missing 0.7% of the data for women's reports on dyadic coping. And so if we want to do dyadic coping for men and women, we have that exact same prevalence rate. So it's 99.3. So it means for that cell, that correlation, we have 99.3% complete data. Right? So we'll scroll down to sample statistics. We have our means and our covariances, but since covariances are not easily interpretable, we also have our correlation matrix here. All right. So here is your another part of your SAMP stat output. A lot of this here, up through here, is going to be some SAMP stat output. And we have means and variances. M+ does not provide your standard deviation. So if that is needed for your manuscripts, then you can just take the square root of the variance. All right. So you have the mean here, you have the variance here. And this is how many people we have, or how many dyads have complete data. All right. So for female dyadic coping, we have 303 out of 305 women providing data on that. We also have min-max, skewness and kurtosis, percentiles, as well as median values. So we will scroll down next, and we want this message to always show up. This tells us that our analysis came to a proper solution. Right? Sometimes you will see error messages here, such as non-positive definite matrices, non-convergence, things like that. So we are really going for model terminated normally. Right? So we have model fit information. So we have the -2 log likelihood, which in these analyses doesn't provide a whole lot of meaning, but when we talk about the common fate with latent interactions, this will become much more meaningful. We have our AIC and our BIC. We have our chi-square test. right? So we have our chi-square test, and we have 1 degree of freedom, and we have a chi-square value of 4.56, which is technically significant, indicated by this p-value. Right? And we have our scaling correction factor for robust maximum likelihood. We might not even need this scaling correction factor. When with regular maximum likelihood, your scaling correction factor is actually 1. And when your scaling correction factor is 1.05 or 1.1 or below, generally you don't need to implement those robust standard errors. So we would actually probably be okay without including robust standard errors here. We could use regular maximum likelihood and not worry about our chi-square being biased or our standard errors being biased. We have our RMSEA, we have our CFI, and we have our TLI. And these 3 are exceptionally common fit indices used in structural equation modeling to indicate whether or not the model is a good fit. The chi-square is also used and almost always reported, but it is extremely sensitive to even minor deviations from our proposed model to our what is actually happening in the data. And so this is not used all that often to evaluate model data fit. We also have the SRMR as another fit index to tell us whether or not we have a good fitting model. So now we will scroll down to model results. So model results will provide unstandardized estimates. So as you can see, because the factor loadings, remember, are by statements, those were fixed to 1. And so we can see in the output that they are indeed fixed to 1. So this tells us, again, we have unstandardized effects here. So unstandardized effects, they can be helpful in some situations, but when we have variables on different scales like we do here, it is difficult to determine, is 0.917, is that a big coefficient, is that a small coefficient? There is no necessarily, there's not a common metric, so this is just in both variables raw metric, and it makes it very difficult to interpret, how big is big, how small is small. Right? So we will scroll down and look at our standardized estimates. So in addition to getting our parameter estimates in standard deviation units, our standardized betas, we also get our standardized factor loadings, which is indicative of the extent to which the common fate latent variable is representative of each partner's reports. So what we want is this dyadic coping common fate latent variable, those loadings to be above 0.70 to indicate, roughly half of the variance is occurring at the dyad level or is shared between dyad member. And so we are good to go. So we are at 0.79 for both male and female for dyadic coping, and for relationship quality, we're at 0.79 for females and 0.87 for males. So this is verification or evidence that we are using a good model, and that the common fate model is appropriate here. If these loadings were, 0.5, 0.4, then that indicates that much more of the variance is at the person level, at the individual level, and is unshared. And other dyadic analyses, such as the APIM, a latent congruence model, a truth and bias model, mutual influence model, would be a better choice. And here is our standardized coefficient. So how this would be interpreted as when a 1 standard deviation unit increase in dyad level dyadic coping is associated with a 0.801 standard deviation unit increase in relationship quality or relationship satisfaction. So this means when couples are able to cope with stress together, that means the couple is happier. So notice in the interpretation that I reference the couple for both variables to be clear that I am estimating and interpreting the effects at the dyad level, because that is what the common fate model is born to do. Right? We also have our residual covariances. And so this means for women, The correlation, the residual correlation between dyadic coping and relationship quality is 0.338 and is significant, right? And then we also have the same thing for males. It's 0.249, but it is not significant, right? P equals 0.07 or 0.08 if you round, right? And so this is the common fate, the baseline common fate model. Right? And if you scroll down a little bit more, you have estimates of our latent variables. So as you see, we are accounting for 64% of the variance in dyadic coping. And we get there in a univariate model by simply just squaring the standardized loading to account for the explained variance. So if you square 0.801, then you will get at 0.641. Of course, there will be some rounding involved. Right, that gets more complicated when you have multiple predictors, but in a single predictor model, you just square that standardized regression coefficient to get the amount of explained variances. So if we scroll down a little bit more, we will get the confidence intervals. Right, so these are going to be symmetric confidence intervals with the robust maximum likelihood adjustment, and it will essentially provide redundant information from what we have up here with our p-values, but it does give us a little bit more of an indication about the spread of our variables, where if these confidence intervals are really, really tight, then that tells us that that we are accurately capturing that specific parameter, and we can say with a lot of confidence that that this interval contains the population parameter. But if our 95% confidence interval is really, really wide, then that tells us we don't have as much certainty, and there's a lot more imprecision in our estimates. So I will scroll down a little bit more to give you a sense of the residual output. And what I would be looking for in the residual output is looking at this residual correlations and the standardized residuals. Because essentially what I am looking at here is the extent to which the correlation between dyadic coping, actually let's do dyadic coping for females and dyadic coping for males. That variable or that number right there, that means that correlation is being underestimated. Negative value means underestimated by 0.004. So a very, very, very small residual. There's a very small difference between what the model expected and what the model found. And so we see a residual correlation of negative 0.05. So we are getting a little bit larger, but again, this is not of substantial worry. Generally, I don't get worried until 0.10 and higher, depending on the model. And then accompanying these values, we have z-scores, right? So we will see here that the z-score for this correlation is actually statistically significant. So we have a critical value of 1.96 for our z-scores, and we can see that this is above that. When looking at the residual correlation matrix, I really look for outlying values, both in terms of z-scores, but also in terms of the correlations. And I don't see anything that is exceptionally large. So I'm not exceptionally worried about model data misfit. Right? And then we have no modification indices because M plus by default will not provide you any modification indices unless that chi-square change by adding in that parameter exceeds 10. So our chi-square was 4. We can scroll back up, 4.56 or 4.57 if you round. Then that means that we're not going to get any modification indices. If you would like to change that, what you can do is in your model command, you can put in a number. So 3.84 is actually the critical value for a 1 degree of freedom test. And we can estimate that. And then we can scroll down to our modification indices, and we will get a whole bunch of proposed modifications you can make to the model. All right. Here is our Tech 1 output. So again, we are labeling all of the parameters. So nu is going to be means, lambda is your factor loading matrix, theta is going to be your residual matrix. And alpha is going to be your intercept, beta is going to be your slope, psi is going to be your variance covariance. And then we have our Tech 4 output, which is going to give us our variance covariance matrix as well as our mean vector. So if we want our variance covariance matrix, we will scroll down and we will have this. This is our estimated variance covariance matrix. All right, and then we have a standard error for each of these values and then a p-value associated with them. All right. So here on this diagonal, we have a variance. So the diagonal elements are going to be variances, and then the off diagonal are going to be covariances. So we have the variance of our dyadic coping common fate latent construct. We have the variance of relationship quality, and then we have the covariance between the two of them. Okay. Then we have our standard errors, and then we have our p-values. Right. So that is a summary of the baseline common fate model in M+, taking a deeper dive into some of these other basics in SEM that you will need to integrate into the model estimation. And from here, you can then build in covariates and you can build out your model to test mediation and moderation. Again, this was just an introductory model into the baseline common fate model. Hopefully this has been helpful, and I look forward to seeing you all in subsequent recordings.